Hello everyone. In this video, we will be discussing two topics in welding. That is strength of welded joints and eccentrically loaded welded joint. First one, we will see the strength of transverse fillet welded joints. So we know that transverse is nothing but the welding which is done in y direction. We call it as a transverse. So in order to determine the strength of the fillet joint, it is assumed that the section of fillet is a right angle triangle ABC with hypotenuse AC making equal angles with other two sides AB and BC. You can able to see, just I'll be going with this particular assumption. Even in the sketch also I'll be showing in the third slide. The enlarged view of the fillet will be shown in the sketch. The length of the each side is known as leg or size of the weld, and the perpendicular distance of the hypotenuse from the intersection of the legs, that is BD, is known as the throat thickness. The minimum area of the weld is obtained at the throat BD, which is given by the product of the throat thickness and the length of weld. You can able to see this. This is a welding example I have taken where axial load is applied and the transverse fillet is applied. Where this is the throat thickness. That is this. You can able to see this is the thickness of the throat, and this is the lap joint, and this is a single fillet and it is a double fillet where one side it is done and is two sides it is done, and there is nothing but the length of the weld. And here I want to say the example what I have considered. So A, B, C, D. So the T is nothing but the thickness, and AB is nothing but the distance from like the thickness from A and till B, from A to B the welding has been done, and this is the reinforcement portions where from the C to A it is having an angle of 45 degree, and this particular portion, the B to D, we will be using to find out the throat value and even the S value. Okay, so let T the throat thickness of BD. So you can able to see BD, it is a throat thickness from the BD I'm talking about, and S is nothing but leg or size of the weld. This is the size of the welding, and T is nothing but thickness of the plate, and L is nothing but length of the plate. L is nothing but length of the plate. So from figure we can find that the throat thickness small t is equal to S into sine 45. That is, I'll just go with the sine. You think that the sine theta is nothing but opposite by the hypotenuse. I'll be going that one. So keeping t in one side, so I'll be writing it as S into sine 45. Sine 45 is nothing but 0.707. So I'll be getting thickness T is equal to 0.707 S. In case if the angle is not 45, in case if it is 50 degree or 65 degree, means whatever the angle we are getting, accordingly we will be writing like sine 45 or sine 55, 60, whatever the angle, that value will be writing up. And the minimum area of the weld or the throat area can be calculated by using this formula: A equal to throat thickness into the length of the weld. So throat thickness is T, and length of the weld is L. So already we know what is the throat thickness. It is 0.707 S. So 0.707 into S into L is nothing but the minimum area of the weld or the throat area. If sigma T is the allowable tensile stress for the weld material, then the tensile strength of the joint for a single fillet weld P equal to throat area into allowable tensile stress, that is 0.707 S into L into sigma T. So the tensile strength of the joint for the double fillet weld, because here we have discussed both single and the double fillet. In case for the double fillet means it is 2 into 0.707 S into L into sigma T. So that becomes 1.414 S into length into the tensile stress. So now we will discuss the strength of the parallel fillet welded joints. Till now we discussed for the transverse fillet. Parallel filament, as I told you in the previous video, where the welding is done along the x-axis. So the parallel fillet welded joints are designed for the shear strength. So consider a double parallel fillet welded joint as shown in the sketch. We have already discussed the previous like concept that the minimum area of weld of the throat area is a thing, but considering 45 degree, it is 0.707 is into L. If T is the allowable shear stress for the weld material, then the shear strength of the joint for the single parallel fillet weld can be written as P equal to throat area into allowable shear stress. That is 0.707 S into L into, we can call it as a tau. Instead of the T, we can go with the tau. So the shear strength of the joint for the double parallel fillet will be 2 into 0.0707 S into L into tau. So that is 1.414 S into L into tau. And here you can able to see this is the combination of the transverse fillet and parallel fillet weld. Even for this cases also we can able to find it out by considering both the transverse fillet and the parallel fillet concept. Now we have the special cases of the fillet welded joints. First one is circular fillet weld subject to the torsion. So for this, let me consider a circular rod connected to a rigid plate by a fillet weld as shown in the sketch, which is shown in the next. You can able to see this one. Let small d is nothing but diameter of the rod, and r is nothing but radius of the rod, and t torque acting on the rod, and s is nothing but size or leg of weld. Small t is nothing but the throat thickness, and capital is the torque. So don't get confused with small t and capital T. And J is nothing but polar moment of the inertia of the section, since it is having circular cross section. So the weld section is nothing but pi LDQ by 4. We know that the shear stress for the material is TR by J. So R is nothing but D by 2. So I'll be writing T into D by 2 divided by pi T DQ by 4. It is pi T DQ by 4. That is the weld section. So finally I'll be getting the stress is equal to 2T divided by pi T D square. So this shear stress occurs in a horizontal plane along a leg of the fillet weld. So the maximum shear occurs on the throat of weld, which is inclined at 45 degree to the horizontal plane. So therefore the length of the throat T equal to S sine 45 degree, that is 0.707 S. Second case we have circular fillet weld subject to the bending moment. Consider a circular rod connected to a plate, a rigid plate by a fillet weld as shown in the sketch. Let small d is the diameter of the rod, and m is the bending moment acting on the rod, and s is the size or leg of the weld, and t small t is the throat thickness. And as usual, z is the section modulus of the weld section. So let me write down that t is equal to pi t d square by 4. That is the weld section is equal to pi t d square by 4, and we know that bending stress, it is bending moment divided by the section modulus. Let me substitute the z value, sorry, the section modulus value. So m divided by pi t d square divided by 4. So bending stress I'll be getting sigma b equal to 4m divided by pi t d square. So this bending stress occurs in a horizontal plane along a leg of the fillet weld. The maximum bending stress occurs on the throat of the weld, which is inclined at 45 degree to the horizontal plane. Therefore, length of the throat T equal to S sine 45 degree to 0.707 S, and the maximum bending stress equal to 4m divided by pi into 0.707 S into T square. After simplification, we can write it down as 5.66 m divided by pi S D square, where m is nothing but bending moment acting on the rod, and S is nothing but size or leg of the weld, and D is nothing but diameter of the rod. And third case, long fillet weld subject to torsion. So for this, consider a vertical plate attached to a horizontal plate by two identical fillet weld as shown in the next sketch. You can able to see something like this. Let T is nothing but the torque acting on the vertical plate, and L is the length of the weld, and S is size or leg of the weld, and small t is the throat thickness, and J polar moment of the welded section. And let me write down the polar moment of inertia for the both the section is 2 into T into L cube divided by 12. So 2 into, sorry, T into L cube divided by 6. So it may be noted that the effect of the applied torque is to rotate the vertical plate about the z axis through its midpoint. This rotation is resisted by shearing stresses developed between two fillet welds and the horizontal plate. It is assumed that these horizontal shearing stresses vary from 0 at the x-axis and the maximum at the ends of the plate. This variation of the shearing stress is analogous to the variation of normal stress over the depth of a beam subject to a pure bending. So therefore shear stress tau is equal to T into L by 2 divided by T into L cube by 6. After simplification, we will be getting shear stress equal to 3T divided by T into L square. Therefore the maximum shear stress occurs at the throat, and it is given by tau max is equal to 3T divided by 0.707 S into L square, that is 4.242 T divided by S into L square. So with this, I'll be winding up this particular video. Thank you.